In section 3.7, we are going to be talking about rational functions. So our parent rational function is f of x is equal to 1 over x. So I'm going to diagram that just real small here. We know that it goes in this quadrant and this quadrant. All right, we have another one now that we're going to add to the ones that you already have. It's 1 over x squared. So this is the squared reciprocal. And what this does is go in this quadrant and this one. So you're always above the x-axis for 1 over x squared. Now, when we talk about rational functions, we have vertical asymptotes that we've had just a little bit that we've talked about. So the denominator cannot ever be equal to 0. So to find those excluded values, you are simultaneously finding the vertical asymptotes where you set the denominator equal to 0, and any x that makes that true will be a vertical asymptote. These are not included in the domain. If it asks you to state the domain, those are not included. Now, with horizontal asymptotes, you're going to be talking about the degree of the numerator and the degree of the denominator. So you have 3 different cases. The first case is that you have the degree of the numerator is smaller than the one on the bottom. So that's BOBO, which stands for bigger on bottom, y equals 0. So your horizontal asymptote would be y equals 0. It's not a number, it's an equation. All right, vertical asymptotes are going to look like x equals. Okay, so those would be the x values that make the denominator equal to 0. If we come back over to the horizontal asymptote and we have the degree of the top is equal to the degree of the bottom, then your horizontal asymptote will be at whatever your leading coefficients in simplified form will give you, so always reduce those. You do need to make sure that your numerator and denominator are in descending order before you determine what your leading coefficient is. Now, this third one we haven't really had up until now, but now that we know how to divide polynomials, then we are able to figure out that if the degree on top is bigger, then we don't have any horizontal asymptote. What we do have is a slant or oblique. Those are the 2 words that you're going to see for this. And this is a different kind of asymptote. For example, if you had one that gave you that as your slant asymptote, your graph might look like this. So this would be y equals x, for example, could be a slant asymptote. So these just kind of make it go cockeyed, okay? It's not going to be vertical and horizontal necessarily. You would have probably vertical and slant or oblique, or you will have vertical and horizontal, but you can't have a horizontal and a slant asymptote at the same time. Those 2 things cannot happen. The way you find this is to do y is equal to the quotient. So once you divide the bottom into the top, whatever your quotient is, without regard to what your remainder is, that would be where your slant and oblique asymptote is. So we'll do some of those. The third thing that can happen is that you can have holes. So these occur when you have common factors in a polynomial numerator and a polynomial denominator that will cancel. So this is where you have a twin on the top and the bottom. And if you cancel that out, then you have a hole at that x value. You find the y value. If that's a question that you're expected to do, then we'll do an example. I don't think they ever ask you that. They just ask you what the x values are. If they do ask you what the domain is, then the x value for whatever that hole is cannot be included in the domain. Also, the y value for wherever that hole is cannot be included in the range. And this last key point right here, I'm going to make this into a star. If a point is considered a hole, it cannot be anything else, which means that it can't be a vertical asymptote, it can't be an x-intercept, it can't exist because it is a hole, which means it is not actually on the graph itself. So on this one page, you have a lot of information that we're going to be using as we work through the next few examples. In this example, it's asking us to find the y-intercept, the x-intercept, vertical asymptote, and then I'm also going to write in a horizontal asymptote. I don't know if it asks for that, but we're going to do it anyway. So as I'm looking through this, the very first thing I want to see and notice is that I can tell that those are in descending order, and I can also look at this very quickly and determine that this degree matches this degree. What that means for me is that my horizontal asymptote is equal to the leading coefficient in the top over the leading coefficient in the bottom. So the leading coefficient in the top is the number 2. The leading coefficient in the bottom is 3, and that will not simplify or reduce. So that's going to be where my horizontal asymptote is. All right, the next thing that I can do fairly quickly and easily is to find a y-intercept. So to find a y-intercept, we let every single x be equal to 0, and we're going to solve for y. So y is equal to 2 times 0 squared plus 3 times 0 minus 5 in the numerator. And in my denominator, I have 3 times 0 squared minus 10 times 0 minus 25. So from this, we know very quickly that these terms are gone. So I'm left with y is equal to negative 5 over negative 25. So that will reduce to a y-intercept of 1/5. So if it wants the number, it would be 1/5. If it wants the ordered pair point, that would be 0, 1/5. Now, x-intercepts and vertical asymptotes work a little differently. At this point, I need to factor this and make sure I don't have any holes. All right, so we have 2x squared plus 3x. I don't know if you all slide and divide or if you use 4 terms. Okay, so you're going to end up factoring that top and factoring that bottom. Go ahead and pause this and see if you can factor both of those and get those 2 factors. So the numerator is going to factor into 2x plus 5 and x minus 1. The denominator is going to factor into 3x plus 5 and x minus 5. Now, if you need help with factoring, I can do that separately. I'm not taking the time to review that here, but I will be more than happy to help you if you need that. So at that point, I can see very clearly that I do not have any common factors, so there are no holes that I have to worry about. Now, to do an x-intercept, we're going to let y be equal to 0, and then we solve for x. So what that means is this. I'm going to do this one time, and then we're going to start using the shortcut. So what that means is that I set this entire fraction equal to 0. Now, the first step to that would be to multiply by this denominator. Well, if I multiply that on that side, it's gone. And if I multiply it over here, then it's still just 0. So we do not write that in there. The shortcut is to determine that you don't have any holes. And then to find x-intercepts, the only thing you've got to worry with is the numerator. So whatever makes the numerator 0, as long as you know you don't have any holes, then you can solve those and come up with your x-intercepts. So we have 2x plus 5 is equal to 0, and we have x minus 1 is equal to 0. So 2x is equal to negative 5, and x is equal to negative 5 halves. So that would be one ordered pair point or value, whichever one it's asking for. And then here we would have x is equal to 1, so we would have the ordered pair point 1, 0. All right, so this, again, to find x-intercepts, you set the numerator equal to 0, and that will give it to you as long as you don't have any holes. You've got to make sure that you check for the holes first. Now, for vertical asymptotes, of course, we're going to set the denominator equal to 0 and solve that. Again, making sure that you don't have any holes. So my denominator would be 3x plus 5 times x minus 5 is equal to 0. And you set each one of those, so we have 3x plus 5 equals 0. So x would be equal to negative 5/3. So that's one of my one of my vertical asymptotes. And then x minus 5 equals 0, so x is equal to 5 would be my other vertical asymptote. So those are equations, not numbers. When we talked about long-run behavior, when we were talking about polynomials, then things either went to infinity or negative infinity. With rational functions, that is not the case. This is asking, does it have a horizontal asymptote and or does it have an oblique asymptote? So as we look at these first 3, this is giving you an example of each one of these long-run behaviors. So the first one has no horizontal asymptote at all. All right, this one would be a slant or an oblique asymptote. And the reason I know that is that the top degree is bigger than the bottom. All right, for the middle one, we have bigger on bottom. All right, this degree of 3 in the bottom is bigger than this degree of 2 in the top. So bigger on bottom, so this is the BOBO, bigger on bottom, then your long run behavior is y equals 0. All right, and then for this last one, we have that both of these degrees match. They don't have to be 2s, they could be 1s, they could be 3s, they can be larger numbers, but as long as those match, then what I'm looking for is the leading coefficient over the leading coefficient. So obviously they're going to have to be in descending order. So the leading coefficient here is a 1, as is here. So this is 1 over 1, which would just leave me with a long run behavior of y equals 1. So as we look at this first example underneath here, the first thing I see is that it's not in descending order. So I have to put the top in descending order. If you accidentally forget to do that, then you're going to have problems because you will end up missing your long run behavior. So putting the top, it changed, the bottom stays the same. Now I'm looking at my degrees. So as I see this, I've got degree of 3 in the top and the bottom. So since it's the same degree, then the long run behavior will be dictated by a horizontal asymptote that has equation y is equal to leading coefficient over leading coefficient. So because it's in descending order now, I have 4 divided by 1, because those are the leading coefficients for both of those. So this has a long run behavior of y equals 4. And what that means is that it's going to level off at the ends. So as x goes to positive infinity and negative infinity, then the y values level off and go to the number 4, because that's where your horizontal asymptote is. Here's another example that you're going to see where it is not in factored form, but what that does for me is make it really easy to find the horizontal asymptote first. So I look at that and notice that it's in descending order and it has the same degree top and bottom. So my horizontal asymptote is leading coefficient of the top over leading coefficient of the bottom. So this gives me 3 over 2, which will not reduce. Horizontal asymptotes are equations. All right, so the next thing that's really easy to do in this format without factoring is to look for a y-intercept. So for the y-intercept, we're going to let x be equal to 0 and solve for y. So that gives me y is equal to the first term, 2 terms in the top disappear, so that's a 5 is left in the numerator, and in the bottom, the first 2 terms are gone, and I have a negative 10. So this gives me a y-intercept at negative 1/2. Now, for the x-intercept, you're going to have your numerator is equal to 0. And for vertical asymptote, you're going to let your denominator be equal to 0. But before we do that, we need to make sure that there are no common factors with this. So take a second and see if you can get those to factor. Again, I'm not going to walk through the steps of factoring these, but my top factors into 3x minus 5 and x minus 1. And the bottom factors into 2x plus 5 and x minus 2. Now, because there are no factors to worry with, then I can jump straight into setting my numerator equal to 0. So that gives me 3x minus 5 times x minus 1 is equal to 0. So that gives me 3x minus 5 is equal to 0. And then x would be equal to 5/3. So that's one of my x-intercepts. My other is x minus 1 equals 0, so that gives me x equals 1. Vertical asymptote is my denominator equal to 0, so that gives me 2x plus 5 times x minus 2. And I set that equal to 0. So for the first one, we have 2x plus 5 equals 0, so that gives me that x is equal to negative 5/2. And the other vertical asymptote would be at x minus 2 equals 0, so that's at x equals 2. So those are the 4 things that it asked me for. That question is now finished. The next question tells me to find any holes. So that doesn't mean that there are holes, but what we're looking for is this factored form. So when I look at the top, I need the factors of negative 3 that add up to give me a 2. So that's going to be x plus 3 and x minus 1. And in the bottom, I have to use the GCF of x, and that leaves me with x minus 1. Now, what happens right here is that I have this and this are twins. So that's where my whole is, and the function that remains is x plus 3 over x. So I'm going to come over here to the right. So I know that I have a whole when x minus 1 is equal to 0, which means the whole has an x value of 1. Now, to find the y value, I set what's left. So y would be equal to 1 plus 3 over 1. So I'm substituting this in to this x and this x because that's what's left of my function. So this will give me a y value of 4. So I have a whole at the ordered pair point 1, 4. So again, 1 can't be in the domain and 4 cannot be in the range. So that would be the only whole that would go with this function. So you have a couple of questions that have just a list that's vertical down through here. It wants to know what the domain is. It wants to know your x and y intercepts. It wants to know only the x value of any holes that you might have. You are asked to find the vertical asymptote, horizontal asymptote, and then oblique asymptote. That doesn't mean that you have all of these things. So if one of these does not exist, then you put DNE in for that. So the first thing I'm looking at with this is to look at my y-intercept, okay, and my horizontal asymptote. Now, for the horizontal asymptote, I have a degree that is bigger on top. So what that means is I don't have a horizontal asymptote. So that's going to lead me into doing the oblique asymptote. So I'm going to do that last. All right, we're going to use the function as it is, and we're going to divide that. So I'm going to leave that for the very last thing that we're going to do, because I also need to look at any holes that we might have. So the next thing I need to do is factor this. So the top has a GCF of x, and then I will factor what remains. And in the bottom, this is going to factor. So take a second and factor those things out. The top ends up giving me x minus 3 and x minus 1. The bottom gives me x minus 8 and x plus 2. So there are no holes. All right, so x values of holes, there aren't any. So that's a DNE as well. At this point, I'm ready to look at my vertical asymptotes and my x and y intercepts. All right, so y-intercept is easy either in factored form or unfactored form. So in this case, if to find the y-intercept, then I'm going to have every single x becomes a 0. Well, everything in the numerator is with an x, so the y-intercept is at an x value of 0 and a y value of 0. I don't know if it wants ordered pairs or if it just wants the number, so be sure that you read that properly. All right, so for x-intercept, I let my numerator be equal to 0. So I have x times x minus 3 times x minus 1, and I set that equal to 0. So there will be 3 x-intercepts. The first one is at x equals 0. The second one is at x minus 3 equals 0, which is x equals 3. And the last one is at x minus 1 equals 0, which is at x equals 1. So the x-intercepts are at 0, 0, 3, 0, and 1, 0. And again, they might just want the actual numbers, and if it just says to separate them with a comma, then it probably does not want the ordered pair points. So be careful to read that. All right, next thing we're going to do are our vertical asymptotes. I'm going to erase this. So for vertical asymptotes, we set our denominator equal to 0. So denominator equal to 0. So I have x minus 8 times x plus 2 equals 0. So this is going to give me x minus 8 equals 0, which means that x is equal to 8 is one of my vertical asymptotes. And the other is x plus 2 equals 0, so x is equal to negative 2. So those would be my two. I think the x equal is already there. If it's not, you need to make sure that you put it there. All right, again, make a note to yourself. These are not included in the domain. Make sure that you leave those out of your domain. All right, so I'm going to erase this, and we're going to draw our number line for the domain. So that's going to be the next thing we do. So for the domain, the things that are going to need to be considered are your x value of any holes, which for us is none, and your vertical asymptotes, which does have numbers. So I need to put a -2 on here, and I need to put a +8 on there. Now, I don't have any holes, so those are the only two restrictions that I have. So that's not included, and neither is this. But that means that all of those numbers are, all of these numbers are, and also all of those numbers. So the domain would be the interval from -∞ to -2. And then we union that with the center, which is -2 to 8. And then we union that with the right-hand side, which is 8 to infinity. So the last thing we have to do is the oblique asymptote. So we're going to take x squared minus 6x minus 16, and we're going to divide that into the numerator, which is x to the third minus 4x squared plus 3x, and then I'm going to add a 0 for the constant that's not there. So as a refresher for what we did when we were dividing, I take x cubed and I divide it by x squared. That gives me x. Now I take that top x and multiply it by each one of the things on the left. So I have x cubed, I have 6x squared, and I have -16x. So the first one is positive, this one would be negative, and so would this one. But then remember, I have to subtract all of those. So I can subtract like this if you can remember to do it. If you're afraid you're going to forget, then you're going to multiply the first one by a negative, the second one by a negative, and the third one by a negative. And then we subtract. So the x cubes are gone. 6 minus 4 gives me 2x squared. 16 plus 3 is going to give me 19x, and then add the +0. I don't know that you're going to need it, but we'll add it anyway. Now at this point, I'm taking this 2x squared, and I'm going to divide it by x squared. So 2x squared divided by x squared is going to result in a +2. So then I multiply each of the left-hand trinomial by 2. So I have 2x squared, I have 12x, and I have 32. So again, the first one is positive, this one's negative, and then this one's negative, but then I have to subtract. So I multiply this one by a negative, multiply this one by a negative, multiply this one by a negative. So the 2x squareds are gone. 19 plus 12 gives me 31x, and then 0 plus 32 is 32. This down here would be my remainder, which I do not care about. What I care about is this up here. So that would be my quotient. So online, when you type this oblique asymptote in, you're going to have y is equal to the quotient, which is x plus 2. Now these questions take time and they take a lot of paper. I know it doesn't look like it here, but I've been erasing as we've gone. So make sure that you have plenty of space to work when you do these questions. So here's another of these questions. So the first thing I'm going to do is look at it and determine my horizontal asymptote and my y-intercept and figure out if I have an oblique asymptote. So the first thing I do is horizontal asymptote. Now the degree of the top is 2, the degree of the bottom is also 2. So what that means is I need that y is equal to the leading coefficient over the leading coefficient. This is the leading coefficient, as is this. So 1 divided by 1 gives me a horizontal asymptote of y equals 1. If I have a horizontal asymptote, then I do not have an oblique. Automatically, you cannot have both of those at the same time. Now, that's not to say that you don't also have a vertical asymptote, because that's a separate thing. So don't jump the gun and say, oh, if I've got one, I've only got one of 3. It's not that way. Horizontal and oblique can't be together, so you have one or the other, but not both. So at this point, we are going to do the y-intercept, because if I plug zeros in where all the x's are, that's going to give me a numerator of 5 and a denominator of 2. If it wants just the number, then you would do that. If it wants an ordered pair point, then you would do this. All right. Now, to figure out wholes, vertical asymptotes, and then x-intercepts, we're going to have to factor. So if we go through and factor these, leading coefficients are 1, which make life a little easier. We don't have a whole lot we have to do. I need factors of positive 5 that add up to give me a negative 6, and that is going to be a negative 5 and a negative 1. And then in the bottom, we're going to have factors of 2 that give you negative 3, so that's going to be negative 2 and negative 1. So at that stage, I am seeing that I have these twins right here, which means that I do in fact have a whole. Now this doesn't want the ordered pair point, it just wants the x value. So this is x minus 1 equals 0. So there is a whole when my x value is 1. So that number would have to go there. Now, with the function that remains, I only have x minus 5 in the top, and I only have x minus 2 in the bottom. All right, so for an x-intercept, I would set x minus 5 equal to 0, numerator equal to 0, x minus 5 equals 0, so x is equal to 5. So that would be either 5 as a number or 5, 0 as an ordered pair point. All right. And then your vertical asymptote is your denominator equal to 0. So that's x minus 2 equals 0, so x is equal to 2. Now, vertical asymptotes cannot be in the domain. So that's one x that will not work. Okay, there's one of them. And then a whole cannot be in the domain. So there's the second one that will not work. Now you can have as many as you need to, but in this case we only have 2 that do not work. So for my domain, I'm going to draw a number line, and on the number line I need the number 1 and I need the number 2, and those are the only 2 numbers that do not work, so everything else will. So everything from there to there, in there, and all the way this way. So your domain then would be the interval from negative infinity to 1, union, the numbers from 1 to 2, union, the numbers from 2 to infinity. So that question is now finished. And again, these take time. Do not rush through these, and be very careful with your calculations and factoring. So the last part of this section, you're going to be writing equations just like we've been doing before. The key with this is to remember that you've got a couple of key points. So you're going to have f of x is equal to, you're always going to have that a value that you're going to check. Okay, a is going to be out there. And then you're going to have a rational function. All right, in the denominator, you're going to have vertical asymptotes, the things that make vertical asymptotes appear. We're going to talk about the multiplicities of those. We had not had that yet, so we're going to talk about that as we go through these examples. All right, in the numerator, you're going to have what give you your x-intercepts. And you already know that those sometimes have multiplicities. All right, so if it's an odd multiplicity for an x-intercept, that means that it crosses through the x-axis. If it is an even multiplicity for an x-intercept, that means it touches it but stays on the same side of the x-intercept. For the multiplicities for vertical asymptotes, if you are approaching an asymptote, for example like this, and this part goes down this way, and this part goes up this way, this is an odd multiplicity. So they go in opposite directions, okay? Now, if you have an even multiplicity, you might have an asymptote here, and then maybe this one goes this way, and this one goes this way. All right, so they're going in the same direction. So if they're even, then they go in the same direction. So your multiplicities work very closely with what your graph is going to give you. So go ahead and copy this first one on your piece of paper, being very careful to put this ordered pair point here. That's important. You need to make sure that you note X equals 4 is a vertical asymptote, and x equals -1 is also a vertical asymptote. You need to make note of the fact that this and this go in opposite directions. This and this also go in opposite directions. So there's a lot of information here. Lastly, you will always be checking an ordered pair point. Typically, it's going to be your y-intercept in order to calculate your a value. So as we start with these questions, the first thing that I generally tell kids to do is determine your x-intercept. So we have an x-intercept at x equals 2. So for my equation, that means that if I have x equals 2, that means that I have to have the factor x minus 2 in my numerator. Now, as I look at it, I'm trying to figure out, are there any other x-intercepts? And that answer is no. And at x equals 2, it cuts through the x-axis. So that's going to have an odd multiplicity. Now, I'm going to default to a multiplicity of 1 with that. It might need to go up, but we'll discuss that when we get there. Next thing I'm going to do is with the blue, we have x equals 4 and we have x equals -1. That means that I have x plus 1 and they go in opposite directions. So again, I'm going to have an odd multiplicity. And then if I have x equals 4 is also a vertical asymptote, then I'm going to have x minus 4 is also a factor in my denominator. And again, they go in opposite directions. Now, the reason I'm saying that those multiplicities might have to be bumped up is if you look at your horizontal asymptote. All right, now this horizontal asymptote says that this is going to keep going this way, and then this one here is going to keep going that way. So I have a horizontal asymptote at y equals 0. So that means that my bigger degree has to be on the bottom. So as long as I have a bigger degree in the bottom, then I'm fine. I don't need to change anything. Now, this has a degree of 2 in the bottom and 1 in the top, so I'm okay and don't need to change anything. So now I'm up to the point where I just need to figure out what my a is. Everything else is finished and worked out. So now I'm going to determine what a is by using the ordered pair point 0, 1, right here, my y-intercept. So I'm going to plug a 1 in where my y is. And I'm going to plug zeros in where all my x's are. So I got 0 minus 2. And then I've got 0 plus 1. And then I have 0 minus 4. So I have 1 is equal to a. Now the fraction ends up being a -2 on the top and then a -4 on the bottom. So -2 divided by -4 is positive 1/2. So then I'm going to multiply both sides by 2 or divide by 1/2, whichever way you want to do that. So you end up with an a value of 2. So my equation is going to be f of x is equal to, you can keep the 2 out front or you can put it in the numerator. It doesn't matter to me. If you have more than just one number, they can go top and bottom with this. It's up to you how you write it though. It'll take it either way. So there's our first graphed equation that we have come up with this function as its description. So here's the second equation that we're going to look at. First thing I'm going to notice is where my x-intercept is. So I have an x-intercept here. I also have this y-intercept here, which we'll use at the end. So this is 0, 2. And of course this one is at 1, 0. All right, next thing I'm going to do is talk about my vertical asymptotes. I have x equals 2 goes here. And I want you to notice that those go in the same direction. So this is going to need an even multiplicity. Those go in the same direction as I approach that asymptote. So it will have to have a multiplicity of at least 2. All right. Then I've got another one over here at x equals -2. And as I'm looking at this one, I've got this is going down, this one's going up, so this one is going to have an odd multiplicity. So at least 1, but it could be a 3 if it needs to be. So as we take into consideration what we have so far, we're going to have f of x is equal to a, which I'm just going to leave out front. All right, my x-intercept is at 1, x equals 1, so this is x minus 1 up here. It cuts completely through the x-axis, so that will be an odd degree. So I'm going to leave it at a 1 unless we need to change it. Then I'm looking at my vertical asymptotes, so I'm going to deal with this one first. We have x minus 2, so that'll be x plus 2, and this one is an odd multiplicity, so I'm going to leave that out of 1. The other one, however, is an even multiplicity, so I'm going to have x minus 2 is going to go here, and that has to be at least 2. Now, it could be 4 or 6 or 8 even if it needed to be, but what dictates that is what is my long run behavior. So as I look at my long run behavior, I can see that it's at y equals 0. So with that being 0, I just need bigger on bottom. So my numerator has a degree of 1, my bottom has actually a degree of 3, so I don't need to adjust my degrees any at all. But now we need to find out our a value, so I use 0, 2, so I put a 2 here, and I'm going to put zeros in everywhere I see an x. And it is important and very much going to cause problems if you forget that squared right there. Because what that does is change the sign on that factor. So in this numerator, I have a negative 1. In the bottom, I have a 2 here. And over here, I've got negative 2 squared. So that gives me a 4. So I have 2 is equal to negative 1/8 a. So if I multiply both sides by negative 8, then that's going to give me an a value of negative 16. So my equation for this function graphed is negative 16, x minus 1, and then I've got x plus 2 and x minus 2 quantity squared. The next graph looks a little different, okay, but you still do it the exact same way. So we're going to start out here. And we need to make a note of the fact that this is at 1, 0, and this will have to have an even multiplicity when I do it. Because it touches the x-axis, it does not cross the x-axis. It is telling us about this y-intercept up here, so it's at 0, 0.4. You can't really tell that in the diagram, so it does tell you what it is. All right, next we've got our our vertical asymptotes. We have one at x equals 3, and we notice that those are going in the same direction, so this will also have an even multiplicity. And then we look at the other one. We've got x is equal to negative 1, and these, of course, go in opposite directions, so this will have an odd multiplicity. So we are ready to start our equation. We have f of x is equal to a that we'll find later. My x-intercept is at x minus 1. That's the factor that goes with it, and it has to be even. So I'm going to put a 2 there and hope that we might not have to switch that, but it can go up to a 4 or 6 if it needs to. So then I go to my vertical asymptotes. We have one at x equals 3. So that's going to be x minus 3, and I know that it has to be also even multiplicity, so I'm going to make that into a 2, knowing that it could be a 4 or a 6 or higher if it needs to be. Next one, I have my x is equal to negative 1, so this is x plus 1 is this factor, and it's an odd multiplicity, so I'm going to leave that at a 1 and see what happens. So in seeing what happens, I have to understand that this continues on and goes this way. This one goes this way. So my horizontal asymptote is at y equals 0. So I just need to make sure that I have a bigger degree on the bottom. If I leave it the way it is, then I have a degree of 3 on the bottom and I have a degree of 2 on top. So that will work. That's bigger on bottom. So the last thing I need to do is use my ordered pair point that they gave me. I'm going to change that into 2/5 just because I prefer to work with the fractions. If you want to work with the decimals, you can do that as well. So I've got 0 minus 1 quantity squared. Do not forget your squareds because those are going to cause problems if you do, because we have a second one there and then we don't have one over here. So as I finish this up, I have 2/5 is equal to, all right, in the numerator I have negative 1 squared, which is a 1. In the bottom I have a negative 3 squared, which is 9, times 1, which is 9. And this is an a, so I'm going to multiply both sides by 9. So those 9s are gone, so I have an a value of 18/5. So I don't need to be freaked out by the fact that that's an odd looking kind of number. All right, so my function has an equation of 18/5. Either keep that out front or you can just extend this and put the rest of it. So I have x minus 1 quantity squared. Down here we have x minus 3 quantity squared and x plus 1. Long section, lots of information in there. Don't procrastinate because these are going to take a while. If you have any questions, come see me.